Gustavson, order bounds for the Rosenfeld-Gröbner basis algorithm.
Thank you. I'd like to thank the organizers for putting this workshop together, asking me to speak. So Rosenfeld-Gröbner algorithm is an algorithm in the theory of differential polynomials, multivariate with multiple derivations, and it's a decomposition algorithm. So I will give some background information, then I'll describe the algorithm, and I'll describe the results. So this is joint work with Alexei and with Gleb Ogudin at Moscow State. So let's just set up where we are working. So we have a differential field K, characteristic 0, M commuting derivations. We have the ring of differential polynomials. We're going to have n differential indeterminates y1 to yn. We're going to fix an orderly ranking on the set of derivatives in this differential polynomial ring. So a ranking is just a total order on the set of derivatives, such that for any derivative, theta u is greater than u, and if u is greater than v, then theta u is greater than theta v. And it's orderly when if the order of u is greater than the order of v, then or if the order of u is less than the order of v, then u is less than v. So we're going to fix an orderly ranking from now on. So that's going to be fixed for everything that we do. So just some terminology going forward, because I find that different people use different notation for some of this stuff. So I just want to have this going forward. So if f is a non-constant polynomial, we're going to let the leader of f is just the derivative appearing in f of highest rank with respect to the fixed orderly ranking. The initial of f is the leading coefficient of f when we write it as a univariate polynomial in the leader. And the separate of f is if we take f and we differentiate it with respect to any of our derivations, the initial of that polynomial is the same no matter what derivation we differentiate it with respect to, and that we call the separate. If we have any set of differential polynomials A, we let L of A be the set of leaders, IA is the set of initials, SA the set of separates, and HA is the set of initials and separates. So this is just, so we all know when I use these terms, we know what we're talking about going forward. Okay, if we have two differential polynomials f and g, we're going to say that f is partially reduced with respect to g if no proper derivative of the leader of g appears in f, and then it's reduced if, in addition, the degree of f in the leader of g is strictly smaller than the degree of g in the leader of g. And so if we have a collection of differential polynomials A, we say that A is auto-reduced if every element of A is reduced with respect to every other element, and similarly partially auto-reduced. And then it's D-triangular if it's partially auto-reduced and the set of leaders is auto-reduced. So obviously every auto-reduced set is D-triangular, and it turns out that every D-triangular set is finite. So we can do reduction with respect to D-triangular sets. So if we have f a differential polynomial and a D-triangular set, we can define a differential partial remainder and a differential remainder of f with respect to a. So the differential partial remainder will denote PD reduction of f with respect to a. So it's a differential polynomial that is partially reduced with respect to a that satisfies this formula. So there is some s in SA infinity such that SF is equivalent to the partial differential reduction by the differential ideal generated by A. And similarly for the differential remainder, now this has to be reduced with respect to A. But now we're allowing things in not just powers of separants, but also powers of initials as well. And so these are not unique. for example, every differential remainder is also a differential partial remainder, but there are algorithms that can compute, given an f and an a, can compute the differential partial remainder and the differential remainder. And so a lot of these algorithms, they have the property that the rank of the differential partial remainder and the rank of the differential remainder will be less than or equal to the rank of f. So that's a very nice property, because since we're dealing with orderly rankings, that means that the order of the differential partial remainder and the order of the differential remainder will also be less than or equal to the order of f. So, and that's going to play a part in the Rosenfeld-Gröbner algorithm, which really uses these differential partial remainders and differential remainders. Okay, so if we have two polynomials f and g, we can define this delta polynomial, which, if you know about Gröbner bases, the delta polynomial is sort of the differential equivalent of the S polynomials in Gröbner basis theory. So if the leader of f and the leader of g have no common derivatives, we just set it equal to 0. And if they do have a common derivative, we set the delta of fg. So if the LCD, the least common derivative of the leader of f and the leader of g, is phi of the leader of f and psi of the leader of g, we define delta of fg to be the separate of g times phi of f minus the separate of f times psi of g. And then we can define a regular differential system is a pair a and h. It's a pair of, it's two sets of differential polynomials a and h. And they have to satisfy these four conditions. So a has to be a D-triangular set. H is a set of differential polynomials that are all partially reduced with respect to a. The set of separates of a has to be contained in H infinity. And then for all pairs of elements of a, we want delta of fg to be contained in this saturation ideal. So what this says is that, so this theta a subscript less than u, so here u is the least common derivative of the leader of f and the leader of g. So that says that we only want to take polynomials of derivatives of elements of a, but of rank strictly less than u. So the idea here is that delta of f and g will always be in the saturation ideal if we replace this with the differential ideal generated by a. And so in order for this to be a regular differential system, we want to be able to get this in a way where we only allow linear combinations of elements whose rank are strictly less than the least common derivative of the leader of f and the leader of g.
This is just being coherent, right?
I'm sorry? Yes, so this is a generalization of coherence. If you know what if you know about coherence, there's a generalization of this. So if A is a coherent autoreduced set, then A comma HA is a regular differential system. Yeah, so this is a generalization of that. Yeah. Okay, and then, so if we have a regular differential system, we let the saturation ideal A by H infinity, we call that a regular differential ideal. And this has a lot of nice properties. So Bouillet and his colleagues proved in 1995 that if we have a regular differential system, then the saturation ideal, which in general would just be a differential ideal, is actually a radical differential ideal. But more importantly for us is Rosenfeld's lemma, which says that if we have a regular differential system, then if we have a differential polynomial p that's partially reduced with respect to a, then p is in this differential saturation ideal, if and only if it's in this algebraic saturation ideal. And this is a really important result because, in algorithmic terms, because this ideal on the right here is an algebraic ideal. and there are many algorithms that allow us to determine membership in an algebraic ideal. So we can test this condition on the right, and that would then allow us to test whether it's in the ideal on the left. So yes.
Sorry. So Rosenfeld, I remember he proved this for coherent systems. So for a regular system, which is more general, the same proof works, or?
Yes, I believe so. I'm not 100% sure,
Okay.
but I believe so. The idea is that the regular differential system takes all of the things that are necessary to get this.
Yeah.
Uh-huh.
I believe it. Yeah.
So if we have a radical differential ideal, we're going to say a regular decomposition is just a finite collection of regular differential systems, such that the radical differential ideal is the intersection of these regular differential ideals. And as we're going to see, every non-trivial radical differential ideal is going to have such a regular decomposition.
You don't require things to be prime or anything. It's just,
No. So this is just radical. Yeah. Okay. So let's talk about the algorithm. So this algorithm is due to Louillet, Lazard, Olivier, and Petitot. I think I pronounced those names correctly. Okay. So here is this is how the algorithm works. So the input is two finite sets f and k. The output. So if it's determined that the saturation ideal, so now we take the saturation ideal, the radical differential ideal generated by f, by k. So if it's determined that 1 is in this saturation ideal, then we return the empty set. Otherwise, the algorithm returns a finite collection of regular differential systems such that the saturation ideal equals the intersection of the saturation ideals of these regular differential systems. So this is what the algorithm does. And so in particular, if k is just the single element 1, then this saturation ideal is just the radical differential ideal generated by f. So what this gives us is a regular decomposition of the radical differential ideal generated by f. So let me just talk about a couple of applications of this algorithm. So the weak differential Mills-Delitzsch says that a system of polynomial PDEs is consistent if and only if 1 is not in the differential ideal generated by f. So what that says is that f is consistent if and only if the output of the Rosenfeld-Gröbner algorithm does not return the empty set. So we have now an algorithmic way of determining whether or not a system of polynomial PDEs is consistent. More generally, we can now test for membership in a radical differential ideal. So what we can do is we apply the Rosenfeld-Gröbner algorithm to our system f. We get a regular decomposition. And then for any polynomial p, we know p is in the radical differential ideal generated by f if and only if the partial differential reduction of p by ai is in this algebraic saturation ideal for every I. And so we have algorithms that allow us to compute this partial differential reduction. And this is an algebraic ideal, so we have an algorithm to test for membership in that ideal. So we can test this condition on the right here. So we can now determine whether or not any polynomial is in a given radical differential ideal. So what's our goal? So that's the setup. So if we have some finite subset A, we're going to let A of A be the order of A. So we take all of the elements F and A, we look at the order of F, and we look at the maximum order. So let's let little h be, if we have two finite subsets F and K, let's let little h be h of F unique K. And our goal is to find an upper bound for the order of the output of the Rosenfeld-Gröbner algorithm based solely on little h, the order of the input, m, the number of derivations, and n, the number of differential indeterminates. So that's what we're going to try to do. Let me give you a little history. So the only previous bound was given by Golubitsky, Kondratьeva, Marino-Mazza, and Alexei. This case was for one derivation, but they worked with an arbitrary ranking, so not necessarily an orderly ranking. They showed that with n differential indeterminates, and if you have if the input has order h, then the output is order at most h times n minus 1 factorial. Okay, so let me give a little bit of the setup to describe how we're going to state the result. So if we have a partially ordered set P, an anti-chain sequence is just a sequence of elements that are pairwise incompatible in this partial order. So we can define a partial order on the set of all derivatives by saying u is less than v if and only if there is some theta such that theta u equals v. So there is then a one-to-one correspondence between theta u and the set n to the m cross n by just pulling out all of the orders of each individual derivation and the index of your indeterminate, and just looking at that in particular, just looking at that. And so we're going to then say a degree of an element of n to the m cross n is just the order of the corresponding element of theta y, and it turns out that every anti-chain sequence of n to the m cross n is finite. Thus, every anti-chain sequence of theta y is finite. So here is the main result that we have. So if we have an increasing function f from the natural numbers to natural numbers, we say that f bounds the degree growth of an anti-chain sequence in n to the m cross n if the degree of the ith element is less than or equal to f of I. And we're going to let LNFM be the maximal length of an anti-chain sequence of n to the m cross n with degree growth bounded by f. And Omar and Alexei have constructed a recursive bound for this number L for all n, m, and f. And I'm not going to go into the details of how they construct that bound, but I'll give some examples for the case that we look at.
I think it's actually equal to the L.
It actually is equal. Okay, so it's not just a recursive bound; they construct a recursive formula for L. Okay, that's even better. Okay, so our result is the following: if we have two finite sets f and k of order h, and we let A be the output of the Rosenfeld-Gröbner algorithm, if L is this number LNFM, where f of I is f sub I being the Fibonacci sequence, then the order of the output of the Rosenfeld-Gröbner algorithm is at most h times f sub L plus 1. So it's at most the order of the input times the L plus first Fibonacci number.
Woo, Fibonacci numbers.
Yeah. So let me just give. I think I have time to just sort of explain where this comes from a little bit. So when you work through the Rosenfeld-Gröbner algorithm, you take a lot of delta polynomials, and delta polynomials usually the order usually doubles when you take delta polynomials. But what ends up happening, the reason the Fibonacci sequence comes up is because in this particular case, we end up seeing that for the particular cases where you have to actually take the delta polynomials, one of the polynomials, like you take delta fg, one of those f or g actually comes from a previous step in the algorithm. So you know that it's the order of that actually is like one less, or one step less than the current one. So instead of order I plus order I, it's order I plus order I minus 1, and so that's why you get the Fibonacci numbers instead of 2 times
the order.
that. So that's where the Fibonacci sequence comes in. Okay, so let me give some examples. So let's look at the case m equals 2 and n equals 1. I should say, in the case m equals 1, so 1 derivation, because we're dealing with an orderly ranking, it turns out that the Rosenfeld-Gröbner algorithm, when you're dealing with an orderly ranking and 1 derivation, the orders don't increase in the Rosenfeld-Gröbner algorithm. So we don't need to look at that case at all, which is pretty nice actually. So when m equals 2 and n equals 1, this is the length is h plus 1. So that means that the orders of the polynomials, well, they're just given by the standard formula for the Fibonacci numbers, is exponential in h. This is the formula. So here's a table of some values for some small values of h. So if the top row would be the orders of your input values, the bottom row would be the maximum order of your output, and it's exponential in h. So very nice result, single exponential for m equals 2, 2 derivations, n equals 1, 1 differential indeterminate. In the case m equals 2 and n arbitrary. So in this case, there's a very nice recursive formula for the longest length of an anti-chain sequence. Is given by this number b sub n, where b1 is h plus 1, and bn plus 1 is given by this formula, h times f sub bn plus 1 plus bn plus 1. So you can work out for an arbitrary n what this length is, and here's a table of some values for some given n's and some given h's. So you can see for small values of n and small values of h's, it gives you a nice result. Very feasible to work with. Here, when you start increasing m, the numbers start going up a little bit, but we can still work out some values. So here are just some values for m equals 3, 4, 5, some small values of n and some small values of h. What we see in particular is that when h equals 1, so first order equations, we can deal with first order equations. That's not that bad. And so for small systems, which in the real world, and when we're applying this algorithm, for most cases we wouldn't be applying this to very large systems, we're able to bound the output with some pretty nice results. Okay, so some examples. Okay, thank you.
Question.
Do you know, so there are several orderly rankings. Do you know which one's the best?
No. So yeah. So this should theoretically work with any one. We didn't really look to see if any one in particular produces better bounds than any of the other ones. And so in order to get a bound on the order, we needed the order of the output to be less than the order of the input. And that's why we needed to work with an orderly ranking. So if you don't have an orderly ranking, you can't bound the order of the output in that case. And maybe you can get around that somehow, but we weren't able to figure out a way to do that. So we're not sure for non-orderly readings. Yeah.
Can I ask you two questions? So this is composition, right? Say you start with a radical differential ideal and you do the algorithm, you know this is composition. The terms in the decomposition, would you be able to find the prime components in those in some of those terms or not necessarily?
I don't.
Would you make your question more precise?
Yes. So you have several terms in this composition, right?
Terms? What do you mean?
I mean these. How do you call
Yeah,
it?
several radical ideals.
Yes, you have several radical ideas, right? So you have do the prime components appear as some of them? Like
Yes.
they do appear. Okay, they do appear.
Yeah. So to get when you have a decomposition, so to get the prime components, so you decompose if you have an algorithm commutative algebra for your particular field and so on. So you decompose each of them into prime components, and so the characteristic sets will be characteristic sets of your prime differential ideals.
Okay.
Now you have more prime components. The actual prime components that are minimal are among those.
That's my question. So they are
They're
among those.
but you might have something extra. But who cares? So you have some extra.
Yeah, I agree.
think it's
But the minimal ones will appear in this list.
Yes.
Okay, that
So
was.
they will appear and they can. That's Uber result. So you can
That's
look
what?
up the Uber result. There is a one-to-one correspondence between prime components obtained from a usual polynomial prime decomposition
Yes.
of the regular ideals and the prime differential components.
Right.
If you allow redundancy.
If you allow
Redundancy.
redundancy.
If you don't
Yeah, redundancy. Yeah.
If you
No, I
don't
agree.
care about
Yeah, because
redundancy.
you can't really identify when you start the minimals with these algorithms.
Yeah, so no minimals, but besides that
Yeah.
but
No.
for that you'll have to do your commutative algebra decomposition. So
Sure,
who
sure.
knows how it's.
Sure. Okay, and second question is also is about what you said, how the Fibonacci sequence appeared.
Mhm.
So you say if you start with F, G, and you want to see what happens with the delta F, comma
Right.
G, right?
Mhm.
And usually, I mean, I guess, why would, so you said that, okay, if you didn't do this Fibonacci sequence, it would double the
Yeah.
order, right?
Yeah.
But I
Not
mean,
exactly, it's still it's less than.
Yes, it's less than that.
cancels it's -1.
it's less, so, but I guess it depends on how apart the F and the G are.
Yeah, but here it's you take the sum because one of them was bounded by
It's
some
like the-
number, the other one is. I mean, it's not double.
No, it's not.
It
Usually
is
it's
the sum actually
the sum of the
orders.
orders of F and G.
Yeah, so it's the sum of the orders, but.
Yeah, okay.
the-
Yeah,
Right.
that's
So,
right.
so
It's the sum of the
basically,
orders,
yeah.
yes.
Basically, so normally the delta polynomial, the order of the delta polynomial is bounded by the sum of the orders of the two things.
Yeah, that's right, okay.
Right. And so normally, if you would take, if you're at the ith step of the algorithm,
Mhm.
say you have the polynomials in the I plus first step would be delta polynomials of the things in the ith step.
Uh-huh.
So
Right.
it would be, so the bounds on the orders of polynomials in the ith step.
Right.
So to get the things in the I plus first step, you would take delta polynomials. Well, that's adding the two, but you just know in general. So it would just be have to be doubling. But really, what we saw was actually going on is one of them is coming from the I step, and the other one is coming from the I minus first step.
And this gives slightly better numbers.
Yes, no, I
Yeah,
agree.
that's,
So,
in
I
the
agree.
past, people were busier with other things, so they didn't pay attention to this.
Yeah, no,
Now
I
is the
see.
time to do it more carefully.
yeah, no, I now understand this part.
Yeah.
Okay, no, thanks.
Other questions? Okay, let's give Richard a hand. The next talk is in 15 minutes.